Hello, good morning, everyone. Can everyone confirm if you are all hearing me clearly?
Yes, sir.
Okay, thank you so much. Thank you for confirming that. I want to welcome everyone to my lecture today. Today, I'm actually going to continue from yesterday's material, and the focus today is basically going to be on time series. Okay, that is going to be the focus today. And I also want to use this opportunity to tell everyone the midterm one will be uploaded by 8 a.m. tomorrow morning. And of course, it's going to be open for 24 hours. It is actually if a program for 1 hour, 30 minutes. The moment you click on start, okay, you're automatically going to be logged out after 1 hour 30 minutes. But you know what, you can start at any time within the 24 hours window. Of course, the latest time for the submission is basically going to be uh on the 25 by 8 a.m., but you can start at any time within the 24 hours window. Okay, so I want to welcome you to my lecture today, and the topic is basically time series analysis. What do we mean by time series? The knowledge of what we've been doing. If I can, if you can recall, I've been working you to sequence of random variables. Of course, that's actually going to be applied to time series data. Okay, so time by time series, we actually means a series of data that are collected over time. Okay, they are collected over time. An example of that could actually be price of stock on consecutive days. You could talk about the cholesterol level of patient. Okay, you could talk about, maybe probably the gas price. Okay, in consecutive days or week, right now in the United States and in the United Kingdom and some places in the world, of course, the gas price are kind of skyrocketed. Okay, so the X1 up to Sn that I call sequence, this only that the source code they actually gonna have is basically gonna be a time component. Okay, that would be a time component. So that is the only thing that is gonna change in what we've been doing. If you look at some textbook, they're basically gonna write XT. Okay, ST actually means the data that you collected over time, but we're using XI here now, okay, which means that I that you are seeing actually represents time, okay? Okay, and why were we interested in time series? A lot of you would be wondering because we basically want to determine the trend, okay? We want to look at the trend, okay? We basically want to see, uh, whether there's going to be an appreciable upward movement or downward movement, or there's going to be kind of stability, okay? So we are actually anxious to be able to know this. Okay, now, uh, I want to say different textbooks like statistics textbook refer to it as time series, but the probability textbook will refer to that as a stochastic process. Of course, when you talk about, I used to tell you that we live in a stochastic world. We live in a probability space, and that is the reason why we got a lot of variations in this world, and we are kind of curious. We basically want to know, okay, whether we can use the variation in the past to explain the variation now, and the variation now to explain the variation in the future. Okay, so take a look at that. Okay, so I will quickly go to some property of time series analysis. And one of that is what we call stationarity. Okay, and we got two types of stationarity. We have what we call strictly stationarity, and we have weakly stationarity. Okay, I'm actually gonna talk about what we mean by that, of course, because of one of the assumptions underlying the use of time series is just like use of time series models is just like, okay, uh assumption is that we want stability. Okay, we want stability. Okay, that is one of the assumptions. So by strictly stationary, we're actually trying to say that if the distribution of the block of length of k of consecutive variable does not depend on I, don't forget the I is basically the time that we talk about. Somebody share with me about the midterm one now. Yeah, the midterm one we cover the week 1 and week 2. Okay, week 1 and week 2. Okay, somebody just chat with me to ask about that. Okay, so we actually, if I have x1, okay, x2 until I get to xn, okay, and I try to look at the and I have another one, x1 plus probably data, s2 plus data until you get to xn plus data. Okay, if they have the same probability distribution, then what we actually means is that that's a strictly stationary. It means it's strictly stationary. That is exactly what we mean. But you know what? We don't in time series analysis, uh, the strictly stationarity assumption may be very, very difficult to meet. And that is the reason why we actually, consider what we call a weakly stationary. And what do we mean by weakly stationary? By weakly stationary, we're trying to say the mean, remain the same over time, and the variance also remain the same over time. I told you at the beginning, we have an assumption of, stability. Okay. Every economy. Okay. This is what we want. You get what I mean? Stability, right? Okay. So the assumption here is that, okay, the mean at different time has to remain the same, and the variance have to be constant over time. And that also implies that the covariance, okay, of xi and xi plus k, when you look at this, when you look at the distance between this guy and this variable, they are k distance apart. Okay, k distance apart. Okay, for instance, if I'm talking about daily data set, maybe I'm talking about daily returns, stock returns. Okay, what I mean is the covariance of x1, okay, and x3 will be the same as the covariance of x2 and x4. That is what I mean. If you look at the distance, is 2. 3 minus 1 is 2. 4 minus 2 is 2. That is what I mean. Okay, when they are k distance apart, we expect their covariance, okay, to actually be that. That's exactly what we mean. Okay, so we are, and that was why we said this does not depend on I, and this does not depend on I. It actually means it's constant over time. Okay, now this is the definition now. You remember the other time when I was walking you through when I said expected value of x1 is mu, expected value of x2 is mu, until you get to expected value of xn equal to mu, each of them returning mu, different sequence returning mu, actually means the mean is the same, okay, for all I, okay, don't forget I said the high is basically the time component. Okay, the time point that I talk about. Okay, and you know what? If you take any pairs of random variable that are separated by the same distance, just like the one I showed you the other time, then we actually can define our covariance. Okay, we're going to call this covariance. Okay, covariance at lag k. Okay, that's a covariance at lag k. Okay, we call that autocovariance function. That is what we call autocovariance function. The autocovariance function at lag k is basically denoted like by that. Okay, so on a weekly stationary now the question now, what we may basically, the other time, yesterday, where I walk you through sampling with replacement and sampling without replacement, you remember that I was able to prove what is the expectation of the mean and what is the variance of the mean. Okay, and of course, I use the idea of linearity of expectation and what we've done before, for us to be able to arrive at the mean and the variance, assuming the sampling with replacement and sampling without replacement. Okay, I think I actually walk you through that. But you know what? We actually want to use that idea now to set up our autocovariance function. You remember what I was working you with before. We did not mention time component. We did not say, I didn't say that the data set were collected over time, but the one we're dealing with today are data point that are actually collected over time. That could be daily, weekly, monthly, quarterly, and so on like that. Okay, now if you take a look at this, we want to find the variance of the sum. You remember that, you remember this to be the formula. Now, if this is the formula now, based on what we've done before, now we basically, don't forget, since the variance, we are assuming the variance of x1, okay, must be equal to the variance of x2, because this guy here is actually talking about the sum of the variances. You know that, right? The variance of x1 plus the variance of x2 until you get so the variance of xn. And you know what, since we expect the variance to be the same over time, they're all going to be sigma squared. And you know what, if they are sigma squared, if I have n numbers of the sequence, I'm basically going to have n sigma squared. But you know what? In time series analysis, the sigma squared, we know we normally use is the same thing as autocovariance function at lag 0. Okay, I'm going to say that again. So this, what I'm telling you now, this guy is more or less like n sigma squared, because we're plugging in, we're trying to say the sigma squared is autocovariance function at lag 0. And I'm going to tell you now why the autocovariance function at lag 0 is actually the variance. Now take a look at this. Okay, when k equal to 0, what happened? That would be this equal covariance xi and si. When you have the covariance of xi and si, that become a variance, right? That become a variance of si, which is sigma squared. Look at that. Okay, somebody share with me now. Let me see. It said, since j equal to 1 plus I, the covariance always the autocovariance has like 1. Yep, 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 you're right. Okay, so take a look at this now. So what I'm trying to tell you now, okay, when the k equal to 0, when the lag is 0, then the autocovariance at lag 0 is basically the sigma squared. I just wanted to take note of that. By plugging in k equal to 0, we're basically going to have that. And that is what we're trying to plug in. Okay, that was how we get that. Take a look at that. And you know what? If you take a look at this guy, that is representing that. Don't forget I told you, okay, that's a notation. Okay, gamma k is a notation for the covariance of xi, okay, sj. Okay, take a look at that. And you know what? This guy here is the n minus k. Look at that. okay, j star from I plus 1 to n, okay, when you take a look at that, okay, so I plus 1, okay, and you continue to go until you get to n, okay, that is the same thing as n minus k, okay, take a look at that. Now we got this guy now, okay, now when you have that guy now, it's basically going to be, this is like the variance of the sum, okay, applying to time series variable. Now another thing we want to, we are not, yesterday when we are trying to find the mean and the variance of a of sample mean, we started from this Torah, right? We started because if I want to get this guy, I'm gonna be needing this guy overhand. You know that, right? This is what we're seeking for. We actually within a time series framework, what we want to do now, we basically want to get the mean of this guy and the variance of this guy. But you know what I just got now is just trying to get the variance of the sum, okay, which is basically this guy. But if I want to extend that to the mean now, okay, I'm just going to come here, okay. If you take a look at what I'm just going to do, I'm just going to come here, I'm going to write variance of summation xi, I start from 1 to n divided by n, okay. That is what I'm actually, this guy here is different from this guy here. Don't forget, what we are actually looking for is the variance of that, okay. That's what we're looking for, right? Okay, so if I do the variance of this now, okay, automatically, by the time I come here, okay, it's basically, what I'm going to have now is going to be I start from 1 to n. I'm just going to have the variance, okay, instead of xi now, okay, I'm basically going to have the x bar, okay. I just wanted to take a look at that and so on like that. So that was what we did, okay, and we basically come here, okay. You're going to see that here initially it was n gamma mu, okay. This was n gamma mu. This one is for the Torah, okay. If I want to do the one for the mean, automatically I'm actually going to have the gamma mu over n, okay. And some of you may be wondering why that, okay. If the variance of s is sigma squared, don't forget the variance of x bar is sigma squared over n, okay. Now that is what you're trying to see here, sigma, that is gamma naught over n. Take a look at that. Now when you now come to this side now, okay, you can see, or just going to divide by n, okay. If you actually want to do the one for the mean, that was why you just have dividing by n, okay. Now what I'm trying to tell you now, okay, if x1 up to xn is a weakly stationary term series, of course the mean, the expected value of x bar, okay, is equal to mu at any point, okay, and the variance of that is that. So that is what we just proved, okay, just like the way we did yesterday, for sampling with replacement and without replacement. Okay, now we now want to go into type of time series model now. Okay, there's something that we call AR1, but let me just tell you, the generally speaking, we have AR of order P. What is the meaning of AR? AR will mean autoregressive model, okay, autoregressive model of order P. What is the idea behind autoregressive model of order P? What does that mean? It actually means I want to relate the current value of a series, okay, with the immediate past, okay, with the previously existing past, okay. It's just like, oh, the price of stock today, okay, and I'm relating the price of stock today with the with the previous existing days, okay. If I relate what happened today with what happened yesterday, that is an arrow for that one, okay. If I relate what happened today, okay, with what happened yesterday and a day before yesterday. I'm basically going to be talking about a arrow of order 2 by autoregressive model. We basically going into the past. We are actually, looking at the relationship between the current value of the series, okay, with the past. That is exactly what we're trying to do. And when you take a look at this now, okay, if we have a Z1 up to Z2, okay, if it's an IID, of course, you know what I mean by ID, okay, identically and independently random variable, and they have a mean 0 and the variance tau squared. Okay, if we now let S0 be any random variable having mean 0, but is independent of Zi, okay, independent of, the X, S0 and the Zi, they are independent. Okay, now we now want to write autoregressive model of order 1. This is the way we're going to write it. If you take a look at this guy here, if I'm talking about the price of stock, okay, this is like a current price, okay, the current price, and this guy here is immediate price of it, immediate price. When I say current price, depending on the units of time, if I'm talking about day, okay, if that current price is the price of stock today, then the X minus, X subscript N minus 1 is the price for yesterday. If I'm talking about, week, okay, if SN is the current the current week price, then the XN minus 1 is immediate week price. Take a look at that. Okay, and you know what, this guy here, which we call rho, okay, is more or less like the contribution of immediate pass to the current pass. Okay, I think I received a chat now. Somebody said, so AR1 just as another time, which is based off the trial time interval. What I'm just trying to, if you take a look at what I have here, okay, I'm trying to tell you, this guy here, the current value of a series, this guy here, immediate past value, okay, and this guy here is like the contribution. You're talking about the contribution of the past to the present value, the contribution of the past value, okay, to the present, to the current one, okay? And this guy here is more or less like a current shock on the system, which I can actually call a white noise, which is a residual, okay? Which is more or less like a residual. In every statistical model, there's going to be a deterministic part and there's going to be a random part. Now I'm going to tell you now, this guy here, that is a deterministic part. Deterministic component. Deterministic component. And this is more or less like random components. And we expect assumption is basically going to be placed on that, on the random component, because we also call that random component, residual, okay, and then we expect the residual to behave like a white noise, okay. We expect residual to behave like a white noise. We have a way to investigate that, okay. So just take a look at that. Now, this is what I call the AR of order 1. If, for instance, if I want to have for order 2 now, what do you think the specification is going to be? Going to be SN, okay? I'm actually going to have row 1 XN, okay? Row 1 XN minus 1, row 2 XN minus 2, okay, plus ZN. Look at the way it is now. This is for a arrow of order 2, which means the current, I'm relating that to the immediate pass and immediate pass. Look at that. We can continue to go, retrospective. You get what I mean? Okay, but you know what? We basically want to focus on the AR of order 1. Okay, we actually, if I have this current value now, since it is related to the immediate past value with the current shock, then we modify the mean. What is the expectation? Okay, which I'm going to show you now. That's exactly what we're trying to do here. Okay, we want to find an expectation. You can see I introduce expectation to all the variables. What are the variable? The Sn, the Sn minus 1, and the Zn. Okay, and you know what? We have an assumption. Don't forget, we have already said here, the Z1 up to Zn as a zero mean. The zero mean, it means expected value of Zn equal to 0. Okay, given any value for 1, 2, and so on like that. And what about the x0 also have a zero mean? Means expected value of x0 equal to 0. That is what it means. Okay, expectation is the same thing as the mean. Okay, now because of that, that's what we're going to impose here now. Okay, that's what you're going to impose. That was why I said that equal to that, and that will be equal to that, because don't forget, we're using the idea of stationarity. We said the mean have to be constant over time. Okay, if the expected value of x0 equal to 0, then it means expected value of Sn will be equal to 0 for all n. That's like applying stationarity. You get that, right? Okay, so that is how we are. So because of that, this equal to 0, this guy equal to 0, then the expected value of Sn will automatically be equal to 0. Take a look at that. Now, if that is the case, what about the variance? If I want to get the variance of Xn, I've already gotten the expectation of Sn, that gives me 0. But if I want to get the variance now, what am I actually going to do? Okay, don't forget the AR of order 1. The specification is actually Xn raw Xn minus 1 plus Zn. Okay, now if I want to find the variance of that, I'm basically going to say the variance of Sn. Okay, don't forget, okay, the variance of Sn is basically going to be the variance of raw Sn minus 1 plus Zn. And you know what? I can basically write the variance of that, or Sn minus 1 plus the variance of Zn. Why do I write that? Because they are independent, we expect the Xn and the Z to be independent, and the covariance will be equal to 0. You don't consider covariance here. Okay, and that's, so if you have that now, the rho is a constant, you know that, right? Then when a constant is going to come out of the variance, it's basically going to be a squared. Okay, and that was how we have this. That was how you got this. Look at that. And don't forget, you have been told, okay, the variance of Zn is a toy squared. Come back here. You are already told. Okay, look at that. You have been, they told you that the variance of that is basically going to be a toy squared. You look at that now, right? Okay, so when you put that into that, okay, that was how this guy is this. Okay, now we are here now, right? Okay, now the variance of Xn equal to that, and you know what? The next we can actually do now. What is the variance of Xn? That's a sigma square, right? Okay, now, and don't forget, this guy and this guy have to be the same. You know why? We have said by weak stationarity assumption, we said that the variance have to be constant over time. The variance of Xn should be the same thing as the variance of Sn minus 1. Okay, we're using the idea of weakly stationarity. So which means I'm going to plug in sigma square here. I'm also going to plug in sigma square here. And that is going to lead to the next one. Oh my God. Take a look at that now. Okay, now you can now solve for sigma squared. Solving for sigma squared, just solve for sigma squared. You're basically going to have that. Okay, now when you have this now, the sigma squared now equal to the toy squared. If you take a look at this, we're basically going to say the variance of error, okay, divided by 1 minus rho squared. Okay, this is the variance of X, the Xn that we just talked about. And this is the same thing as a gamma 0. Okay, the autocovariance are like 0. And we are now saying that the variance has to be non-negative. That is a the weekly stationarity requirement. And because of that, the rho has to be between -1 and 1. Okay, imagine if rho equal to 1. If rho equal to 1, what happened? The variance will be indeterminate. Indeterminate. Okay, indeterminate when rho equal to 1. With a 1 situation where rho equal to 1. Because you remember, mathematically speaking, when the denominator of a fraction equal to 0, then it is undefined. You know that, right? Okay, now that is how we got that. Now you know what we want to do now. For a arrow of order 1, we've already obtained the mean. Okay, the expected value of xn, we obtained that to be equal to 0. We've already obtained the expression for the variance, okay, which is this guy here. The next thing that we want to talk about now is the covariance. Okay, we want to talk about the covariance now. Okay, and you know what? We want to talk about this covariance for, you can talk about covariance, the autocovariance. We're going to call that autocovariance. The autocovariance when the variables are k lag apart. Look at that. Okay, when you look at n plus k and n, okay, n plus k minus n, it actually means k, right? So which means these are k lag apart. Now, if they are k lag apart, we want to find the covariance of that. And don't forget, your xn is basically an a arrow of order 1 model, which is basically Sn minus 1 rho plus Zn. Okay, now what you want to do now, we are actually want to get Xn plus K. What are you going to do? Introduce K. Going to be N plus K, right? Rho, okay, Xn plus K minus 1 plus Zn plus K. Now, if this guy is this, then introducing plus K, you're going to have that. Now, if I want to find the covariance of that now, then I'm actually going to plug in the whole of this. That is basically what you see here. What is it representing? It's representing this guy here. Okay, and this is Sn, right? Now, that was how we find ourselves here. Okay, now the next thing you're going to do now, okay, this guy, okay, you're gonna use this guy now on this guy. Okay, that is what you have here. And you're going to use this guy on this one too. Look at that. You use it on this. You also use it on that. And that will give you this and this. And you know what? Z and X, they are independent. Then the covariance will be equal to 0. You have been told the Z and N are independent. The covariance of that will be 0. Because of that, you don't have this guy anymore. You only have this guy here. Take a look at that. That is exactly what you have now. Okay, now when you have this guy now, okay, now let us now somebody share with me now. Let me see. Say, why are we allowed to take the p out of the parenthesis in step 2? Oh, that's a good question. Because it is constant. Okay, this guy here is a constant. Okay, then a constant is going to come out. Does that make sense to you now? A constant is going to come out. Okay, because rho is a constant. I told you the other time, constant is basically going to come out. I hope the person that chat with me understand the question now. Okay, okay, yeah, so that is that. Okay, so the next thing that I'm actually want to say now, okay, if you have this guy now, okay, when your k equal to 1, okay, when you plug in k to be equal to 1, okay, now you're basically going to have this. Okay, from here, k equal to 1, you're going to have xn. Okay, it's going to be xn. And when you have covariance of the variable that is 0 apart, that's a variance. You know that, right? It's going to give you this. The covariance of SN. Okay, XN, you are referring to variance within is the same variable. Covariation within itself is a variance. Okay, that was why you have this guy now. Okay, that guy equal to that guy. And of course, the variance is sigma squared. Okay, because of that, I'm going to say this guy here will give you this. Okay, because you can be asked to derive. So that guy is going to lead to that. Okay, this is for K equal to 1. Okay, well, what if you let K to be equal to 2? What is going to happen? When K equal to 2, you're going to have this. Okay, and the moment you have that now, okay, now take a look at this. When you put that, it's going to lead to this, right? Okay, K equal to 2, put 2 here. That would be n plus 2 minus 1. That would be n plus 1, right? And this guy, okay, is the one we derive here to be this. Okay, if you bring that to join with rho, that would be rho square sigma square. Look at that. That is recursive. Okay, now if you want to go, so this is what I'm trying to tell you now. This is for situation where K equal to 1. This is for situation where K equal to 2. Now, if I want to continue, I want to go into K equal to 3. Let's assume, let me go down. That will be n plus 3, right? Xn, okay, equal to rho covariance Sn plus 2 Xn. Now, if I want to get that, right? What did I get for this covariance Sn plus 2, comma Sn? What did I get? Okay, I got this guy, right? So I'm going to put rho squared, sigma squared. What about this guy? Rho. What do I get now? Okay, this guy now is basically going to give me rho raised to power 3, okay, sigma squared. Now that's a pattern. I want you to take a look at something now. When K equal to 1, we got this for K equal to 1. We got this for K equal to 2. Okay, for K equal to 3, you're basically going to get rho 3 sigma squared. Now, when you continue to K, this is going to be the general formula then. Look at that. That would be a generalization. So take a look at that. Okay. Now, then it means for a arrow for that one, we've been able to prove that the expected value of Sn equal to that, and the covariance of 2 times series variable that are K distance apart equal to that. That is what we just determined, where you can use the formula to get for K equal to 1, for K equal to 2, and so on like that. So take a look at that. Okay, now the next thing is monotonicity of expectation. What does it mean? When U is less or equal to V, you know, this guy actually means V greater or equal to U. That is what it means. Okay, when you take the expectation, okay, that pattern is still going to be maintained. That is why if U is that, then expectation of them will be less. That is just what we mean. Okay, there's no issue with that. So that's so easy. Okay, now the second objective of today is what we call Markov inequality. I'm also going to walk you through Shapeshift inequality. And what do we use Markov inequality to do? Now, when you take a, we have from Markov inequality, we have a non-negative random variable y. It has to be a non-negative, okay, and a positive real number lambda. So the probability of a non-negative random variable y greater or equal to a positive real number is less or equal to the ratio of the mean of the y to the constant lambda. Now, in real life practical situation, what do we use Markov inequality to do? Okay, you know what I'm trying to say. But when we say let us use income, okay. Now we assume that income is non-negative. You know that, right? Income is non-negative. I think you know that, right? Okay, we're trying to say, for example, say 1/5, okay, of the population, okay, you know, we say not more than not more than 1/5 of the population, okay, has, more than 5 times the average income. The average income, that's what we mean. Okay, not more than 1/5 of the population as, more than, 5 times the average income. If I want to generalize, I'm going to say not more than 1/lambda of the population as more than lambda times the average income. Okay, that's exactly what we mean. We're using this to place a bound. Okay, we actually use a Markov inequality. Of course, we find ourselves in a world that is stochastic in nature. We are not the same in terms of weight, in terms of income. Okay, we have different income class. And that is the reason why Markov inequality is actually going to be so useful. Okay, now this is it. Only that if you want to find Markov, the mean, the expected value of y of that particular non-negative variable must exist. Okay, now this is the proof. Okay, of this, you're going to start with lambda high indicator y, which is less or equal to y. Then you take the expectation of that. You're going to find yourself there. Okay, now to the Shapeshift inequality. Okay, to the Shapeshift inequality. The Shapeshift inequality is trying to tell you if I have a random variable x, okay, and the mean of that random variable x is mu, the probability of the square difference of the, the square of the difference between the random variable s and the mu greater or equal to a particular constant lambda will be less or equal to the expectation of the square of that difference divided by the lambda, which is more or less like the variance divided by lambda. What do we use this for? We use Shapeshift inequality. The Shapeshift inequality is very similar to 68, 95, 99.7, 99.7% empirical rule. You remember in statistics, we have 68, 95, 99.7 empirical rule actually means when the random variable x follow normal distribution, 68% of the observation are actually going to fall within one standard deviation. 95% will fall within 2 standard deviation, and more than 99% will fall within 3 standard deviation. That is for empirical rule. Empirical rule is actually is used for normally distributed data. But how for when the data set is not normally distributed, then what is the alternative for what can replace empirical rule is a Shapeshift inequality. Okay, the Shapeshift rule is basically going to tell us, okay, within 2 standard deviation, 75% of the observation will lie within 2 standard deviation, while 88.9% of the data set will lie within 3 standard deviation. Don't forget, applying Shapeshift rule, okay, the shape of the distribution does not matter. Okay, but if you want to apply empirical rule, the shape of the distribution really matter. It has to be normal. Okay, I want to tell you what the empirical rule does is the same thing as what the Shapeshift inequality rule also doing. Okay, I just wanted to take note of that. Okay, now this is the formula now. Okay, for that. Okay, now the last thing for today is what we call the law of large numbers. I just want to summarize that. Large numbers in statistics, what do we mean? We mean as n tend to infinity. Okay, when you have a sufficiently large sample, what happened? Okay, what happened? We're looking for situation whereby this guy here is basically going to converge to mu. Okay, this is the true value. That's a population mean, right? What can we actually do before this mean can converge to that? Okay, and we believe that using the Shapeshift inequality rule, take a look at what we're doing here. This is telling us, okay, what is the probability? Okay, you are trying to measure the probability of the absolute difference between this mean and the true mean. Okay, the probability that it should be greater or equal to delta, where delta is a very small number, is less or equal to the variance of that divided by the delta squared. That is exactly what it's talking about. Okay, the fact remain that we're actually looking for a way of convergence. Okay, we don't study the entire population, and we're trying to say we take a sample, right? Okay, and don't forget, what can we do for the sample means that we got, to be very close to the true value, to the population mean we're looking for. And what we're trying to do here is to be able to investigate as sample size increases, what happen. That's exactly what we're trying to do. Okay, so the variance, don't forget, the variance of the mean is sigma squared over n. Okay, if I plug that in here, okay, if I plug that in here, I'm actually going to get this guy here. Look at that. Sigma squared divided by n delta squared, because of the variance of x bar, don't forget, sigma squared over n, and that's exactly what we get here now, right? So take a look at that. Okay, so now the convergence that we're talking about is, what do we mean by convergence? Oh, something actually lead to something. What do I need to do? If we want a sample mean to converge to the true mean, what are we basically going to do? Okay, now here a sequence of random variables z1 up to z2 converges in probability, because we have different form of convergence. We could have some that converge in probability. We could have some that converge in distribution. We could have some that converge in quadratic mean and so on like that. But the convergence that we're talking about now is convergence in probability. Okay, and the probability convergence is all like, okay, and we are targeting A, okay, and we have a sequence of Zn, okay, before we can actually say the Zn converges to A as n tends to infinity, we want to look at the probability of that, the probability of the absolute difference between the sequence and a constant A greater or equal to delta. That probability must tend to 0. You know why? It means if I want to change this, if I want to rewrite this, I'm going to say the probability of the absolute value of Zn minus A less or equal to delta. Okay, now this must tend to 1. Okay, because you know why? Delta is very, very small and it is greater than 0. Okay, so that is a probability convergence as n tends to infinity. As n tends to infinity means you are taking a very large sample, and because of that, if that happened, I'm basically going to say the Zn actually converges to A in probability. That's exactly what we mean. And we're trying to say, when the n tend to, when I take a large sufficient sample, then I expect my sample mean to converge to the true values of the mean, which is the population mean. That is exactly what we mean. Okay, and that happened in probability, because for every delta greater than 0, I was able to find that the probability of the absolute difference between the sequence and the A, okay, greater or equal to delta, actually tend to 0. Okay, so take a look at that. Okay, so I think that is all what we need in this material. You can read up every other one, we don't necessarily need them. Okay, so that is basically where I'm actually going to stop today. Okay, but before before I go, okay, before I go, you can read up every other one in case you don't really understand what that means. They are just basic probability rules. And of course, the expectation independent that we have done before. Before I go today, I want to say there's going to be a midterm one tomorrow, and it will be posted at 8 a.m. to the canvas, and it's going to be left open for 24 hours, and you can start at any time within the 24 hours window. And you know what, the moment you click on start, your time is going to be running out, and you will automatically you will automatically be logged out. Somebody said, do you remember getting on work too? I want to say, let me tell you this: the moment you focus on the midterm one practice, okay, because the exam the midterm one exam is going to follow the pattern that that you have in the midterm one practice. Okay, I'm going to say this again. Okay, if you focus more on the midterm one practice questions, okay, the pattern of the exam we follow that. Okay, the pattern of the exam, okay, we follow that. Not the same question, of course, you know that. Not the same question, but the pattern we actually follow that. Okay, so and those who have sent the evidence of accommodation later, they actually going to have extended time. Okay, they basically going to have extended time. And today, watch out. I'm going to send you. I'm going to share the exam instruction. Okay, the instruction that you basically going to follow in tomorrow's exam. Watch out today through the announcement section. I'm actually going to communicate with everyone. You're going to see the instruction. You get what I mean? Okay, so like I said, midterm one practice questions, okay, is very, very crucial. And the homework one solution, you don't need homework two solution here. I'm going to say this again. The homework one solution and the midterm one practice questions, oh my God, it's actually going to go a long way. Okay, and that was why I released those practice questions and I walk you through those questions. But let me tell you this: number 5 in the midterm one practice question, that area will not be tested. Number 5 is talking about sampling with replacement and sampling without replacement. It will never be. It won't. You can't see that question tomorrow. But we advise that what you have done, the cardinality, the independence, you know, the getting the PMF, change of variable, they are very, very crucial. And you know what? Believe you're actually going to succeed. Okay. I used to tell my student, anytime they are writing exam, believe, even if you have not had A before in any course in statistics, believe you're actually going to get A. Okay. The only thing you just need to do, you just need to take your time, study what we've done, particularly focus more on the midterm one practice question and the homework one solution. Students who have passed through me before, I know they will really understand the way I do things. Okay, focus more on midterm one practice question, the homework one solution, and what we've done before. You're basically going to be fine, and believe you're actually going to succeed. Okay, believe even if you have not scored A before in any statistics course, believe in yourself. This time around is something that can be done. It's something that you actually achieve. And I used to tell students, success in life is not falling down, but staying down. Why? I'm seeing success as the ability to rise after many falls. Pick yourself up, pick yourself up, pick yourself up. Believe you're actually going to succeed. Figure just take your time. Take your time. If you don't get it, at one attempt, continue to do enough practice. You're basically going to get there and you're going to be the best in the world. Okay, this is where I'm actually going to stop today. There's not going to be any lab tomorrow, because the exam, is set for tomorrow. Like I said, 8 a.m., you're actually going to receive a notification for this exam. Follow instruction, and you know what the exam is going to be on for 24 hours. You can start at any time within the 24 hours window, but only that when you click start, your time is going to be running out. Okay, and you know what, those who do not have accommodation letter, they're going to spend 1 hour 30 minutes, and those who have sent the evidence of accommodation letter, they basically going to have an extended time. Please follow instruction and believe in yourself. You're actually going to succeed. Make sure you stay safe and have a lovely week, a lovely day, a lovely weekend. Bye for now, everyone. Thank you too. Yeah, thank you, everyone.
Thank you.
You're welcome. Thank you, everyone. Thank you so much.